On a cold December morning, long before sunrise reached the cities below, a team of astronomers gathered inside a quiet control room illuminated only by computer screens and blinking status lights. Across the room, conversations were hushed, not because something had gone wrong, but because something important was about to begin. Nearly 1.5 million kilometers away from Earth, beyond the Moon and far outside our planet's atmosphere, the James Webb Space Telescope had turned its giant golden mirror toward a destination unlike any other. It was not looking at the edge of the observable universe. It was not studying galaxies formed shortly after the Big Bang. Instead, it was observing a place much closer to home, a place that astronomers had dreamed about visiting for generations. That destination was Alpha Centauri, the nearest star system to Earth. For most people, for light years sounds unimaginably far away. A modern passenger jet would need millions of years to reach it. Even the fastest spacecraft ever built by humanity would take tens of thousands of years to complete the journey. Yet on a cosmic scale, Alpha Centauri is practically our neighbor. If the Milky Way galaxy were reduced to the size of Earth, Alpha Centauri would be only a few meters away from our solar system. For centuries, humans have looked at these stars without realizing what they truly were. To the naked eye, Alpha Centauri appears as a bright point of light in the southern sky, but hidden behind that single point are multiple stars locked together in a gravitational dance that has lasted for billions of years. Scientists have long believed that if humanity ever travels beyond the solar system, Alpha Centauri may become the first destination. For decades, telescopes around the world studied this nearby stellar system. Space observatories measured its brightness, tracked its motion, and searched for evidence of planets orbiting its stars. Yet even with all that effort, many questions remained unanswered. The stars themselves are extraordinarily bright, making it difficult to detect smaller objects nearby. Imagine trying to spot a tiny candle placed directly beside a giant spotlight. That is the challenge astronomers face when searching for planets around stars. The intense light overwhelms instruments and hides faint details that might otherwise be visible. This is where James Webb changed everything. Unlike previous telescopes, Webb was designed to observe the universe primarily in infrared light. Instead of seeing only visible brightness, it could detect heat. Objects invisible to ordinary telescopes could suddenly reveal themselves through their thermal signatures. Dust clouds, distant planets, and structures hidden within stellar systems could potentially emerge from the darkness. As the first observations were processed, researchers expected to see exactly what their models predicted. Alpha Centauri A and Alpha Centauri B are both remarkably similar to our own Sunday. They orbit each other over a period of about 80 years while a smaller red dwarf star, Proxima Centauri, travels much farther away. Scientists believed they understood the basic layout of the system. Yet the earliest results suggested that reality might be more complicated. Small infrared anomalies began appearing in the data. They were faint, barely noticeable at first, but they appeared repeatedly. Some researchers suspected instrument noise. Others believed the telescope was detecting dust particles scattered throughout the system. The data was reviewed again and again. Teams checked calibration settings, examined processing methods, and searched for possible mistakes. But the signals refused to disappear. Every time the observations were analyzed, the same strange patterns returned. The discovery did not immediately make headlines. In science, extraordinary claims require extraordinary evidence. Researchers remained cautious. However, excitement quietly spread among astronomy teams around the world. Alpha Centauri was supposed to be familiar territory. If something unexpected was appearing there, it meant there were still major discoveries waiting in our own cosmic backyard. Suddenly, one of the most studied star systems in history became one of the most intriguing. Scientists who had spent years modeling planetary formation around nearby stars began revisiting their assumptions. Could hidden planets be influencing the environment? Could dust structures be forming in ways nobody predicted? Could there be objects orbiting the stars that previous telescopes had completely missed? Nobody knew the answers yet, but for the first time in years, Alpha Centauri felt mysterious again. As more observations arrived, the sense of anticipation grew stronger. Every new image carried the possibility of revealing something entirely new. Somewhere within those streams of data might be clues about how planetary systems form, how stars evolve, and whether Earth-like worlds could exist around our nearest stellar neighbors. What began as a routine observation was slowly becoming something much more significant. The James Webb Space Telescope had only just begun its investigation of Alpha Centauri, and already scientists were realizing that the closest star system to Earth might still be hiding secrets that nobody expected to find. To understand why the James Webb observations attracted so much attention, we first need to understand what Alpha Centauri actually is. Many people imagine a single star similar to our Sun, but the reality is far more fascinating. Alpha Centauri is a multiple star system, a miniature stellar neighborhood located approximately 4.37 light-years from Earth. At its center are two large stars known as Alpha Centauri A and Alpha Centauri B. These stars orbit one another in a slow gravitational dance that has continued for billions of years. Alpha Centauri A is slightly larger and brighter than our Sun, while Alpha Centauri B is somewhat smaller and cooler. If a person could somehow stand on a planet orbiting one of these stars, the other star would often shine in the sky brighter than any planet appears from Earth. The view would be unlike anything humanity has ever witnessed. For centuries, astronomers wondered whether planets could survive in such a complex environment. In our solar system, planets orbit a single star. The gravitational influence is relatively straightforward. But in Alpha Centauri, two large stars constantly move around one another, creating changing gravitational forces throughout the system. Early theories suggested that stable planets might struggle to form there. Yet later simulations revealed something surprising. Not only could planets exist around Alpha Centauri A and B, but some regions might actually be quite stable for billions of years. This discovery transformed the system into one of the most promising targets in the search for potentially habitable worlds. Far beyond the two main stars lies a third member of the family, Proxima Centauri. Although often discussed separately, it is gravitationally connected to the larger system. Proxima is a small red dwarf star, much dimmer than our Sun and thousands of times less luminous than Alpha Centauri A. If our Sun were replaced by Proxima Centauri, daylight on Earth would resemble a permanent twilight. Yet despite its faint appearance, Proxima quickly became one of the most famous stars in astronomy. In 2016, scientists confirmed the existence of a planet orbiting it, Proxima b. This discovery immediately captured global attention because the planet resides within the star's habitable zone, the region where temperatures could potentially allow liquid water to exist. The announcement triggered enormous excitement. Suddenly, the nearest known exoplanet to Earth was not dozens or hundreds of light-years away. It was right next door in cosmic terms. Headlines around the world described Proxima b as a possible second Earth. Scientists, however, remained cautious. Red dwarf stars are notorious for violent stellar activity. Powerful flares can erupt from their surfaces without warning, releasing tremendous amounts of radiation into space. Any planet orbiting close enough to receive warmth from such a star may also be exposed to intense radiation storms. Whether life could survive under such conditions remains one of the biggest unanswered questions in modern astronomy. When James Webb turned toward Alpha Centauri, researchers hoped to learn more about all three stars and the environment surrounding them. Unlike earlier telescopes, Webb could search for subtle heat signatures that might reveal hidden structures. Dust rings, asteroid belts, and even undiscovered planets could potentially leave traces detectable in infrared wavelengths. Scientists knew the system better than almost any other beyond our solar system, yet they also understood that many mysteries remained unresolved. The closer astronomers looked, the more complicated Alpha Centauri seemed to become. One reason the system fascinates scientists is that it offers a glimpse into what humanity's future may look like. If future generations develop technologies capable of traveling between stars, Alpha Centauri will likely become the first destination. Concepts such as laser-driven probes, fusion-powered spacecraft, and even interstellar colonies are often designed with Alpha Centauri in mind. Unlike distant stars hundreds of light-years away, this system feels almost reachable. Not today, not tomorrow, but perhaps someday. Every new piece of information gathered by James Webb helps transform Alpha Centauri from a distant point of light into a real place with real landscapes, real planets, and potentially even environments where life might exist. As researchers continued studying the incoming data, they realized they were no longer simply observing a nearby star system. They were investigating a future frontier. Somewhere among those three stars could be rocky worlds, strange planetary systems, and phenomena never before observed. The nearest stellar neighborhood in the galaxy was beginning to reveal details hidden from humanity since long before our species existed. And with every new observation, Alpha Centauri became a little less familiar, and a lot more mysterious. For decades, astronomers pointed some of the world's most advanced telescopes toward Alpha Centauri, hoping to uncover its secrets. They used ground-based observatories perched on remote mountaintops, giant radio telescopes spread across deserts, and powerful space telescopes orbiting above Earth's atmosphere. Each generation of instruments revealed something new, yet every discovery also highlighted how much remained hidden. The closer scientists looked, the more they realized that Alpha Centauri was surprisingly difficult to study. Ironically, its greatest advantage, being the nearest star system to Earth, was also one of its greatest challenges. The stars were so bright that their light overwhelmed many observations, making it extremely difficult to detect smaller objects nearby. Planets, dust clouds, and other faint structures were often lost within the overwhelming glare. Imagine standing in a dark field at night and trying to spot a tiny firefly hovering directly beside a massive stadium floodlight. The firefly may be there, but the floodlight's brightness completely dominates your vision. This is similar to the challenge astronomers face when searching for exoplanets around nearby stars. Even large planets reflect only a tiny fraction of the light produced by their parent stars. Earth itself, viewed from another solar system, would appear billions of times dimmer than the Sun. Detecting such worlds requires extraordinary sensitivity and incredibly sophisticated instruments. This is where the James Webb Space Telescope entered the story. Unlike the famous Hubble Space Telescope, which primarily observes visible and ultraviolet light, James Webb was designed to focus on infrared wavelengths. Infrared light is invisible to human eyes, but it carries valuable information about heat throughout the universe. Every object with a temperature above absolute zero emits infrared radiation. Stars emit enormous amounts of it. Planets emit it. Dust clouds emit it. Even extremely cold objects drifting through deep space can reveal themselves through faint infrared signatures. By studying these wavelengths, Webb could observe features that other telescopes often missed entirely. The telescope itself represented one of the most ambitious engineering projects in human history. Its primary mirror consists of 18 gold-coated hexagonal segments working together as a single giant mirror over 6 meters wide. The observatory operates nearly 1.5 million kilometers from Earth at a location known as the Second Lagrange Point, or L2. There, a giant sunshield the size of a tennis court protects its sensitive instruments from heat emitted by the Sun, Earth, and Moon. The observatory must remain extraordinarily cold to detect faint infrared signals from distant objects. Even tiny amounts of unwanted heat could interfere with observations. Every component was designed with precision that pushed modern engineering to its limits. When Webb finally became operational, astronomers quickly realized they possessed something unlike any telescope that had existed before. It could peer through thick clouds of cosmic dust. It could detect galaxies formed shortly after the birth of the universe. It could analyze the atmospheres of distant exoplanets by studying starlight passing through them. And perhaps most importantly for Alpha Centauri, it could reveal structures hidden within the glare of bright nearby stars. Suddenly, regions that had remained invisible for decades became accessible for investigation. Scientists approached Alpha Centauri with cautious optimism. They did not necessarily expect a revolutionary discovery. The system had been studied extensively, and many researchers believed they already possessed a reasonably accurate understanding of its overall structure. Webb's role, they assumed, would mainly be to refine existing knowledge and perhaps identify smaller details missed by previous observations. Yet science has a long history of surprising even its most experienced practitioners. Again and again, the most important discoveries emerge when researchers investigate something they believe they already understand. As Webb's instruments gathered data, astronomers began processing enormous amounts of information. Every observation produced streams of measurements requiring careful analysis. Teams around the world examined images, compared infrared signatures, and checked results against theoretical models. At first, everything appeared normal. The stars behaved largely as expected. Their brightness, temperatures, and orbital positions matched previous observations. But then subtle anomalies began to emerge. Certain infrared signals appeared stronger than anticipated. Faint structures seemed to exist where models predicted relatively empty space. The differences were not dramatic enough to make headlines immediately, but they were intriguing enough to capture the attention of experts studying the system. Researchers became increasingly interested in understanding what they were seeing. Was it simply dust? Could hidden planetary material be scattered throughout the system? Were there previously undetected objects influencing their observations? Nobody knew yet. What was clear, however, was that James Webb was revealing details that earlier instruments had either missed entirely or lacked the sensitivity to confirm. The nearest star system to Earth was beginning to look more complicated than scientists had imagined. For decades, Alpha Centauri had seemed familiar, a neighboring stellar system that astronomers believed they understood relatively well. But as Webb continued collecting data, that sense of familiarity began to fade. Beneath the bright glow of its stars, hidden details were emerging from the darkness. The telescope was not merely improving existing observations. It was opening an entirely new window into our nearest cosmic neighbor. And soon, one particular discovery would force scientists to take a much closer look at what might be hiding there. The first indication that something unusual was happening did not arrive with a dramatic announcement or a stunning image splashed across computer screens. Instead, it appeared as a subtle inconsistency buried within streams of infrared data. To most people, the numbers would have looked meaningless, but to the scientists studying Alpha Centauri, they represented something that should not have been there. At first, nobody was alarmed. Strange readings appear frequently in astronomy. Telescopes are incredibly sensitive instruments, and countless factors can influence observations. Cosmic rays strike detectors. Background radiation interferes with measurements. Software occasionally introduces artifacts during data processing. Most anomalies disappear once researchers investigate them more closely. This one did not. The unusual signal appeared as a faint excess of infrared radiation coming from regions around the stars where scientists expected relatively little activity. The increase was small, almost insignificant at first glance, but it remained consistent across multiple observations. Researchers carefully compared the data against theoretical models. They checked instrument calibration. They reran processing algorithms. They examined every possible source of error they could think of. Yet no matter how many times they repeated the analysis, the signal continued to appear. It was weak, but it was real. Inside astronomy departments and research institutions, excitement began to spread quietly. Nobody wanted to jump to conclusions. Scientific history is filled with examples of discoveries that vanished under closer examination. But there was something intriguing about this particular anomaly. Alpha Centauri was not some distant, poorly understood region of space. It was the nearest stellar system to Earth. If unexpected infrared emissions were present there, they might reveal something important about how nearby planetary systems evolve. Researchers started asking questions. Was the signal coming from dust? Was it evidence of asteroid collisions occurring somewhere within the system? Could hidden planetary bodies be influencing the surrounding environment? Each possibility carried significant implications. One theory suggested that vast clouds of microscopic dust particles might be responsible. Dust is far more important in astronomy than most people realize. Entire planets form from dust. Rings around planets consist largely of dust and ice. Young star systems often contain enormous disks of material left over from their formation. When observed in infrared light, dust becomes particularly visible because it absorbs stellar radiation and re-emits it as heat. If Alpha Centauri contained more dust than expected, Webb would be exactly the kind of telescope capable of detecting it. However, the distribution of the signal raised new questions. The infrared emissions did not perfectly match what researchers expected from ordinary dust clouds. Some areas appeared brighter than models predicted, while other regions seemed unusually quiet. The patterns hinted at a more complex environment. Astronomers began exploring alternative explanations. Perhaps gravitational interactions between unseen objects were shaping the material. Perhaps there were structures within the system that previous telescopes had never resolved. Every answer seemed to generate additional mysteries. As weeks turned into months, the investigation deepened. Teams from different countries examined the findings independently. Researchers compared Webb's observations with decades of historical data collected by earlier telescopes. In some cases, they discovered subtle hints that similar phenomena may have existed all along but had been too faint to confirm. Webb's extraordinary sensitivity was allowing scientists to see details that previous generations of astronomers could only speculate about. It was as if someone had finally turned on a light inside a room humanity had been exploring in near darkness. What made the discovery particularly exciting was not the possibility of a single object or phenomenon. It was the realization that Alpha Centauri might be far more active and dynamic than expected. The nearest stellar system to Earth was beginning to reveal layers of complexity hidden beneath its familiar appearance. Dust, heat, gravitational interactions, and perhaps even unseen worlds were all becoming part of the investigation. Scientists were no longer simply studying stars. They were piecing together an evolving environment that could hold important clues about the formation of planetary systems throughout the galaxy. The deeper researchers looked, the clearer it became that this unexpected signal was only the beginning. Something within Alpha Centauri was producing patterns that existing models struggled to explain. Whether the answer involved dust, planets, or something entirely unforeseen remained unknown. But one thing was becoming increasingly obvious. The James Webb Space Telescope had uncovered a mystery in humanity's own cosmic backyard, and solving that mystery would require looking far deeper into the system than anyone originally planned. As scientists continued investigating the mysterious infrared signals detected by James Webb, one explanation kept returning to the center of the discussion: dust. At first, this might sound disappointing. After all, when most people hear about a strange discovery in a nearby star system, they imagine hidden planets, alien worlds, or some extraordinary cosmic phenomenon. Dust seems almost mundane by comparison. Yet in astronomy, dust is often where the most important stories begin. Entire solar systems are born from dust. Rocky planets like Earth are built from dust. Even the atoms inside our bodies were once part of ancient clouds of dust drifting through space billions of years ago. To astronomers, dust is not an obstacle, it is a clue. The problem was that Alpha Centauri did not appear to contain the amount of dust Webb seemed to be detecting. Existing models predicted a relatively stable and mature stellar system. Alpha Centauri A and B are estimated to be between 5 and 6 billion years old, slightly older than our Sun. Over such immense periods of time, much of the leftover material from planetary formation should have either been incorporated into planets, ejected into interstellar space, or destroyed through countless collisions. Scientists expected some dust to exist, but not enough to produce the unusual infrared signatures appearing in Webb's observations. As researchers examined the data more carefully, they noticed something even stranger. The dust did not seem evenly distributed. Certain regions appeared denser than expected, while other areas remained relatively clear. The pattern suggested that something was actively influencing the material. Dust drifting freely through space tends to spread out over time, but the structures Webb observed hinted at organization. Something was shaping the environment. Something was controlling where the dust gathered and where it did not. One possibility involved asteroid-like bodies colliding within the system. In our own solar system, collisions occur constantly. Most are small and harmless, involving tiny fragments of rock and ice. But occasionally larger impacts occur, producing enormous amounts of debris. If similar events were taking place within Alpha Centauri, they could generate fresh dust clouds visible to Webb's infrared instruments. Yet calculations suggested that a few random collisions alone might not fully explain the observations. The pattern seemed too persistent and too widespread. Another theory pointed toward hidden planets. Massive planets exert powerful gravitational influence on their surroundings. As they orbit their stars, they can shepherd dust into rings, gaps, and complex structures. Saturn provides a perfect example. Its gravity shapes countless particles into spectacular rings that stretch hundreds of thousands of kilometers through space. On a larger scale, unseen planets around Alpha Centauri could potentially be sculpting the dust detected by Webb. If true, the dust itself might be acting like a map, revealing the presence of worlds that remained invisible to direct observation. This possibility generated enormous excitement. For decades, astronomers have searched for planets around Alpha Centauri A and B. Because the system is so close, any confirmed Earth-like planet would instantly become one of the most important discoveries in human history. Future generations might one day attempt to visit such worlds. Yet despite years of searching, definitive evidence remained elusive. Webb's observations were not proof of hidden planets, but they hinted that something more complicated than simple dust clouds could be shaping the environment. Researchers also considered the possibility that the system's unique structure played a role. Unlike our solar system, Alpha Centauri contains multiple stars. The gravitational interactions between Alpha Centauri A and B create conditions unlike anything planets experience around a solitary star. Over billions of years, these interactions could influence asteroid belts, dust disks, and planetary orbits in ways scientists do not yet fully understand. The very presence of two Sun-like stars may be responsible for creating patterns that challenge existing models. As computer simulations became more sophisticated, scientists began testing different scenarios. They added hypothetical planets. They adjusted dust densities. They altered orbital configurations. Some simulations produced results surprisingly similar to Webb's observations, while others failed completely. Yet no single model explained everything. The mystery remained frustratingly incomplete. Every answer solved one problem while creating another. What made the situation so fascinating was the realization that Alpha Centauri still had the power to surprise us. Humanity has studied these stars for generations. We know their brightness, their masses, their motions, and their approximate ages. Yet beneath that familiar exterior, the system was revealing hidden layers of complexity. The nearest stellar neighborhood in the galaxy was proving that even the places we think we understand best can still hold secrets. As more observations arrived, one conclusion became increasingly difficult to ignore. The dust itself was not the real mystery. The real mystery was what was creating it, shaping it, and keeping it organized. Somewhere within Alpha Centauri, forces were at work that scientists did not yet fully understand. And if those forces involved undiscovered worlds, then James Webb might be standing at the beginning of one of the most important planetary investigations ever conducted. As the mystery surrounding the dust deepened, attention gradually shifted toward a far more exciting possibility. What if the strange structures detected by James Webb were not simply random clouds of debris? What if they were evidence of planets hiding within the Alpha Centauri system? For decades, astronomers had searched for such worlds. The idea was irresistible. Somewhere around the nearest stars to Earth, there could be rocky planets with oceans, mountains, and skies unlike anything humanity had ever seen. Yet despite countless observations, proving their existence remained incredibly difficult. The brightness of the stars concealed many potential targets, leaving scientists to search indirectly through tiny clues hidden within the data. Finding planets around distant stars is rarely straightforward. Even large planets are almost invisible when viewed beside the stars they orbit. Imagine trying to photograph a grain of sand next to a lighthouse from hundreds of kilometers away. This challenge becomes even greater when dealing with nearby stars like Alpha Centauri A and B. Their intense brightness floods instruments with light, drowning out faint objects that might otherwise be visible. As a result, astronomers often rely on indirect techniques. They look for tiny movements in a star caused by a planet's gravity. They search for slight dimming when a planet passes in front of its star. They analyze subtle patterns within dust and debris that may reveal the influence of unseen worlds. The strange infrared structures observed by Webb suddenly became extremely interesting because planets often leave fingerprints without ever being directly observed. Throughout the universe, astronomers have discovered planetary systems where rings of dust contain unusual gaps, spirals, and concentrations of material. In many cases, these features are created by planets moving through the surrounding debris. Their gravity acts like an invisible sculptor, shaping the environment over millions of years. If similar processes were occurring within Alpha Centauri, the dust web detected could be silently revealing the presence of hidden planets. Scientists began running increasingly sophisticated computer simulations. They created virtual versions of Alpha Centauri and inserted hypothetical planets of different sizes and orbital distances. Some were Earth-sized worlds. Others resembled Neptune or Jupiter. Researchers then watched how these planets influence surrounding dust over millions of simulated years. Certain results were remarkable. In some scenarios, planets naturally produce structures surprisingly similar to those appearing in Webb's observations. The match was not perfect, but it was intriguing enough to keep the idea alive. Among the most exciting possibilities were rocky planets orbiting within the habitable zones of Alpha Centauri A and B. These are regions where temperatures might allow liquid water to exist on a planet's surface. In our solar system, Earth occupies such a zone. Too close to the sun and water evaporates. Too far away and it freezes. The habitable zone represents a delicate balance. Since Alpha Centauri A and B are somewhat similar to our Sun, scientists have long suspected that comparable regions may exist around both stars. If rocky planets occupy those zones, they could become some of the most important targets in the search for life beyond Earth. Yet caution remained essential. Astronomy has taught researchers to be patient. Many apparent planetary detections have disappeared after further investigation. Signals that initially seemed promising sometimes turned out to be stellar activity, instrumental noise, or entirely different phenomena. The scientific community resisted making bold claims without overwhelming evidence. Still, the possibility lingered. Every new dataset collected by Webb seemed to hint that Alpha Centauri was more populated and dynamic than previously believed. What made the situation especially compelling was the system's proximity. Most exoplanets discovered so far orbit stars dozens, hundreds, or even thousands of light-years away. They are fascinating scientifically, but reaching them would be nearly impossible with foreseeable technology. Alpha Centauri is different. Although still unimaginably distant by human standards, it remains the nearest stellar destination beyond our solar system. Any potentially habitable planet discovered there would immediately become one of humanity's most significant long-term exploration targets. As the investigation continued, researchers found themselves facing an extraordinary possibility. The unusual infrared signatures, the dust structures, and the complex gravitational environment might all be connected. Somewhere within the system, hidden worlds could be shaping everything Webb was seeing. The evidence was not yet conclusive, but the idea could no longer be ignored. For the first time in years, scientists felt they might be standing on the edge of a discovery capable of transforming our understanding of the nearest stars in the galaxy. And if planets truly were hiding there, the next challenge would be figuring out exactly where they were concealed. Ironically, one of the biggest obstacles preventing scientists from discovering hidden worlds in Alpha Centauri was the very thing that made the system so attractive in the first place: its stars. Alpha Centauri A and Alpha Centauri B are among the brightest stars in the night sky. To casual observers, that brightness makes them easy to find. To astronomers searching for planets, however, it creates an enormous challenge. Every observation is flooded with stellar light so powerful that faint objects nearby can disappear completely. A small rocky planet reflecting starlight becomes almost impossible to distinguish from the overwhelming brilliance surrounding it. Even James Webb, with all its advanced technology, must carefully work around this problem. To understand the difficulty, imagine standing in front of a car with its headlights aimed directly at you on a dark road. Now imagine trying to spot a tiny insect flying only a few centimeters away from those headlights. The insect may be there, but the glare makes it nearly invisible. This is essentially what astronomers face when searching for planets around bright stars. In some cases, the difference in brightness between a star and an Earth-like planet can be billions of times greater. The planet becomes lost inside the star's light like a grain of dust inside a spotlight. Over the years, scientists developed increasingly sophisticated techniques to overcome this problem. Special instruments known as coronagraphs were designed to block portions of a star's light, allowing telescopes to examine nearby regions more effectively. Advanced software could subtract known patterns of stellar glare from images, revealing faint structures hidden beneath. Researchers became experts at distinguishing real objects from optical artifacts. Yet even with these tools, Alpha Centauri remained one of the most difficult systems to study in detail. James Webb introduced new possibilities. Its infrared vision allowed scientists to focus not only on visible light but also on heat. Some planets, especially larger ones, emit detectable infrared radiation. Dust clouds warmed by nearby stars also become visible in these wavelengths. By examining the system through multiple infrared filters, researchers could build a more complete picture of what was happening around the stars. Features that remained invisible in traditional observation sometimes emerged clearly in Webb's data. As scientists processed more observations, they noticed something fascinating. The regions closest to the stars remained challenging, but farther out, subtle structures began to appear with increasing clarity. Dust concentrations, faint thermal signatures, and possible debris features became easier to identify. While none of these observations directly revealed a hidden Earth-like planet, they demonstrated that Alpha Centauri contained far more complexity than earlier telescopes had been able to detect. The glare was no longer completely hiding the system's secrets. Researchers also realized that the stars themselves might be affecting the environment in unexpected ways. Because Alpha Centauri A and B orbit one another, their gravitational influence constantly changes throughout the system. At certain points in their orbit, dust and debris experience different forces than they would around a single isolated star. Over millions or billions of years, these interactions can shape the architecture of the entire system. Belts of material may shift. Dust clouds may become concentrated in certain regions. Even planetary orbits could evolve in ways that differ dramatically from what occurs in our solar system. The more scientists learned, the more Alpha Centauri seemed to challenge assumptions. What initially appeared to be a relatively familiar stellar neighborhood was revealing itself as a dynamic and evolving environment. Webb's observation suggested that the nearest stars to Earth still held surprises despite centuries of study. Every new dataset seemed to expose another layer hidden beneath the glare. For astronomers, this was both frustrating and exciting. Frustrating because the brightness of the stars continued to conceal many answers. Exciting because each improvement in observation techniques brought new discoveries within reach. Somewhere beyond that overwhelming light could be planets, asteroid belts, dust rings, or entirely unexpected phenomena waiting to be revealed. The challenge was enormous, but so was the reward. As researchers continued refining their methods, one thing became increasingly clear. The strange signals James Webb had detected were not going away. If anything, the evidence was becoming stronger. Hidden behind the brilliance of Alpha Centauri's stars, something was shaping the system in ways scientists had not fully anticipated. The question was no longer whether there was a mystery. The question was how deep that mystery truly went, and whether the answers might be found around the system's most intriguing member, a small red star known as Proxima Centauri. While much of the attention surrounding Alpha Centauri focused on its two sun-like stars, many scientists were becoming increasingly interested in a smaller and far more unpredictable member of the system, Proxima Centauri. At first glance, Proxima appears insignificant compared to its larger companions. It is a red dwarf star, much smaller, cooler, and dimmer than our Sun. If Alpha Centauri A is a bright cosmic lighthouse, Proxima is more like a glowing ember in the darkness. Yet appearances can be deceptive. Despite its modest size, Proxima Centauri may be the most extreme and dangerous star in the entire system. Red dwarf stars are the most common type of star in the Milky Way. In fact, most stars in our galaxy are red dwarfs. They burn their fuel slowly and can survive for trillions of years, far longer than stars like our Sun. Because they are so abundant, astronomers believe countless planets may orbit them throughout the galaxy. This makes understanding red dwarfs incredibly important. If life exists elsewhere in the universe, there is a good chance it may exist around stars similar to Proxima. Yet these stars have a darker side. Unlike our relatively stable Sun, red dwarfs are often highly active. Powerful magnetic fields twist and tangle across their surfaces. When those magnetic fields suddenly reconnect, they release enormous bursts of energy known as stellar flares. Some of these flares can be thousands of times more powerful than anything ever recorded from the Sun. Within minutes, vast quantities of radiation are blasted into surrounding space. Any nearby planet caught in the path of such eruptions may face conditions far more hostile than scientists once imagined. This became particularly important after the discovery of Proxima b, located within the star's habitable zone. Proxima b immediately became one of the most exciting exoplanets ever found. The planet appears to be roughly Earth-sized and orbits closer to its star than Mercury does to the Sun. Under normal circumstances, such proximity would make a planet unbearably hot. However, because Proxima is much cooler than the Sun, its habitable zone exists very close to the star. At first, this seemed like excellent news. A nearby Earth-sized planet within a habitable zone sounded almost too good to be true. Then researchers began studying Proxima's behavior more closely. Observations revealed that the star experiences frequent and violent flaring events. Some eruptions can dramatically increase the star's brightness in a matter of minutes. During these events, intense ultraviolet and X-ray radiation floods the surrounding region. Scientists began asking an uncomfortable question. Could a planet orbiting so close to such an active star retain an atmosphere for billions of years? If powerful stellar storms continuously blasted the planet, its atmosphere might gradually erode into space. Without a protective atmosphere, liquid water could disappear, and surface life would face enormous challenges. James Webb's observations offered scientists a valuable opportunity to investigate this problem. By monitoring infrared emissions and stellar activity, researchers hope to better understand how Proxima influences its surrounding environment. The results reinforce the idea that this tiny red star is far from peaceful. Evidence suggested that energetic events continue to shape conditions throughout the region. Every flare acts like a cosmic storm, altering the environment around the star and potentially affecting any planets that happen to orbit nearby. Yet despite these dangers, Proxima remains one of the most fascinating objects in the galaxy. Some scientists argue that life could still survive there under the right conditions. Perhaps thick atmospheres protect planetary surfaces. Perhaps powerful magnetic fields shield planets from radiation. Some researchers even speculate that life, if it exists, could thrive underground or beneath vast oceans hidden from the harsh stellar environment above. The more scientists study Proxima, the more they realize that the answer is far from simple. As James Webb continued gathering data, astronomers found themselves confronting a surprising possibility. Alpha Centauri was not merely a nearby star system containing a few interesting planets. It was a laboratory where some of the most important questions in astronomy could be explored. How do planets survive around active stars? Can habitable worlds exist in environments very different from our own? And perhaps most importantly, could life emerge under conditions once considered impossible? The nearest stellar system to Earth was becoming increasingly complex. Hidden planets, mysterious dust structures, powerful stellar flares, and unexpected infrared signals were all pieces of a puzzle that scientists were still struggling to assemble. And as the investigation continued, one question began to dominate discussions around the world. If planets truly existed throughout the Alpha Centauri system, could any of them actually support life? Few questions capture the human imagination more powerfully than the possibility of life beyond Earth. Every discovery of a new planet, every strange signal from deep space, and every observation made by advanced telescopes eventually leads back to the same fundamental question: are we alone? As James Webb continued studying the Alpha Centauri system, scientists found themselves asking that question more often than ever before. The system's proximity made it unique. If life exists anywhere beyond our solar system, Alpha Centauri could be one of the first places humanity might someday investigate directly. The search for life, however, is far more complicated than simply finding a planet. A world can exist and still be completely hostile to biology. Venus, for example, is often called Earth's twin because of its similar size, yet its surface is hot enough to melt lead. Mars once possessed rivers, lakes, and perhaps even oceans, but today it is a frozen desert exposed to intense radiation. Habitability depends on a delicate balance of countless factors. A planet needs the right temperature, a stable atmosphere, access to liquid water, and protection from dangerous radiation. Even then, there is no guarantee that life will emerge. Scientists examining Alpha Centauri began focusing on these requirements. Around Alpha Centauri A and B, theoretical habitable zones exist where Earth-like temperatures might be possible. If rocky planets orbit within these regions, they could potentially maintain liquid water for billions of years. Because both stars are similar to the Sun, some researchers believe planets there may experience conditions not entirely unlike those on Earth. This possibility alone makes Alpha Centauri one of the most important targets in modern astronomy. Yet the reality is far from simple. Unlike our solar system, Alpha Centauri contains multiple stars influencing one another through gravity. Over long periods of time, these interactions may affect planetary climates and orbital stability. A planet that appears habitable today could experience dramatic environmental changes over millions of years. Scientists continue running simulations to determine whether Earth-like worlds could remain stable within such a system. Encouragingly, many models suggest that they can. Attention also remained fixed on Proxima b. Since its discovery, the planet has occupied a strange position in scientific discussions. On one hand, it is the nearest known exoplanet to Earth and resides within its star's habitable zone. On the other hand, it orbits an active red dwarf capable of producing powerful radiation storms. The debate continues. Some researchers believe Proxima b may have lost much of its atmosphere long ago. Others argue that a sufficiently strong magnetic field could shield the planet from stellar activity, preserving conditions favorable for life. James Webb's observations did not provide a definitive answer, but they offered valuable clues. By studying the system in infrared wavelengths, scientists gained a better understanding of the environment surrounding these stars. Dust distributions, heat signatures, and stellar behavior all contribute pieces to the larger puzzle. Every observation helps researchers determine whether planets within Alpha Centauri are likely to be barren worlds or places where life could potentially survive. The search for extraterrestrial life has changed dramatically over the past few decades. Not long ago, scientists did not even know whether planets existed around other stars. Today, thousands of exoplanets have been discovered throughout the galaxy. Some are gas giants larger than Jupiter. Others are rocky worlds similar in size to Earth. A growing number appear to orbit within habitable zones. With every new discovery, the possibility that life exists elsewhere becomes increasingly difficult to dismiss. For many astronomers, Alpha Centauri represents more than a scientific target. It represents hope. If habitable worlds exist there, they are not hidden on the opposite side of the galaxy. They are located in our own stellar neighborhood. Future generations equipped with technologies far beyond our own may one day send probes to investigate them directly. Images of alien oceans, mountains, or skies could theoretically arrive from Alpha Centauri long before any other star system. As the James Webb Space Telescope continued revealing new details about the nearest stars to Earth, scientists found themselves standing between certainty and possibility. They knew that planets could exist there. They knew that habitable zones were present. They knew that the system contained mysteries still waiting to be solved. What they did not yet know was whether life had ever taken hold within those distant worlds. That answer remained hidden among the stars. But with every new observation, humanity moved one step closer to finding out. One of the most important moments in science occurs when observations refuse to match expectations. Throughout history, some of humanity's greatest discoveries began with data that simply did not fit existing theories. The discovery of Neptune, the expansion of the universe, and even the existence of black holes all emerged because scientists encountered evidence that challenged what they thought they understood. As James Webb continued sending information from Alpha Centauri, researchers found themselves facing a similar situation. The system was not behaving exactly as their models predicted. For years, astronomers had developed detailed simulations describing how Alpha Centauri should look and behave. These models incorporated everything scientists knew about the stars, their masses, temperatures, ages, orbital paths, and gravitational interactions. Using powerful computers, researchers simulated billions of years of evolution, attempting to reconstruct how the system formed and how it changed over time. Many of these simulations suggested that Alpha Centauri should be relatively calm and stable today. Yet Webb's observations hinted at a more complicated reality. The unexpected infrared signatures continued to challenge assumptions. Dust appeared in places where little dust was expected. Certain regions displayed thermal characteristics that did not align perfectly with existing predictions. While none of these findings overturned established science, they forced researchers to reconsider details they had previously taken for granted. Sometimes the differences were subtle. Sometimes they were difficult to explain. But together they suggested that Alpha Centauri might possess hidden complexities not fully captured by current models. Scientists began revisiting old datasets collected by previous observatories. Information that once seemed unremarkable suddenly gained new significance when viewed through the lens of Webb's discoveries. In some cases, researchers found faint hints of unusual structures that earlier telescopes had lacked the sensitivity to confirm. What once appeared to be noise now looked like potential evidence. It was as though Webb had revealed the first few pieces of a puzzle that had been sitting unnoticed for decades. The challenge became even greater because Alpha Centauri is not an isolated star. The constant gravitational interaction between Alpha Centauri A and B creates a dynamic environment unlike our solar system. As the two stars orbit one another, their influence extends throughout the system. Dust, asteroids, comets, and planets all experience subtle gravitational effects that accumulate over millions of years. Small changes can eventually produce large consequences. A planetary orbit may shift slightly. A dust belt may become distorted. Debris may gather into structures nobody initially predicted. Webb's observations suggested that some of these long-term processes could be far more important than researchers previously realized. Computer simulations became increasingly sophisticated as scientists attempted to reconcile theory with observation. New variables were introduced. Planetary scenarios were tested. Dust dynamics were modeled in greater detail than ever before. Some simulations produced results that resembled Webb's findings surprisingly well, while others failed completely. The process was slow and meticulous, but it highlighted something fundamental about science: understanding does not emerge from certainty. It emerges from questioning assumptions when evidence demands it. Perhaps the most exciting aspect of this process was the realization that Alpha Centauri remained capable of surprising humanity. Despite being the nearest stellar system beyond our own, it still contained unanswered questions. This served as a reminder of how little we truly know about the galaxy around us. If mysteries remain hidden within our nearest cosmic neighbor, how many more secrets are waiting among the hundreds of billions of stars scattered throughout the Milky Way? As researchers refined their theories, they began to view Alpha Centauri differently. It was no longer merely a nearby destination or a target for future exploration. It had become a testing ground for our understanding of planetary systems themselves. Every anomaly, every unexpected observation, and every unexplained structure represented an opportunity to learn something new. The system was forcing scientists to rethink ideas that had seemed secure only a few years earlier. Yet even as old models were being rewritten, another realization was emerging. The discoveries made by James Webb were not only important for understanding Alpha Centauri. They were also laying the foundation for something much bigger. Future generations may not be content with observing these stars from afar. Someday, humanity may attempt to reach them. And if that day comes, the information being gathered now could become the first chapter in the history of interstellar exploration. Long before humanity built airplanes, crossed oceans, or walked on the moon, people imagined journeys that seemed impossible. Every generation has looked toward a distant horizon and wondered what might exist beyond it. Today, Alpha Centauri occupies that role. It is the horizon of our era, the nearest destination beyond the solar system, and perhaps the first star system humanity may someday attempt to reach. As James Webb continued revealing new details about this neighboring system, scientists were not simply studying distant stars. They were gathering information that future explorers might one day depend upon. The challenge of reaching Alpha Centauri is almost impossible to comprehend. Light itself, the fastest thing in the universe, requires more than 4 years to travel between Earth and the system. Modern spacecraft are far slower. Voyager 1, the most distant human-made object ever launched, has been traveling through space since 1977. Even after nearly half a century, it has not traveled even 1% of the distance required to reach Alpha Centauri. At its current speed, Voyager would need tens of thousands of years to arrive. Such timescales make traditional space travel impractical for interstellar missions. Yet that has not stopped scientists from thinking about solutions. Around the world, researchers are already developing concepts for spacecraft that could travel far faster than anything humanity has built before. Some proposals involve powerful lasers that would push tiny probes to a significant fraction of the speed of light. Others explore advanced propulsion systems powered by nuclear fusion, the same process that fuels stars. While many of these technologies remain experimental, they demonstrate an important fact: humanity is no longer merely dreaming about interstellar travel. For the first time, serious scientific efforts are beginning to explore how it might actually be achieved. This is where James Webb's observations become especially valuable. Before sending any probe toward another star, scientists need to understand the destination. What planets exist there? Are there dangerous regions filled with debris? How active are the stars? What environments might future spacecraft encounter? Every piece of information collected today helps answer these questions. Webb is effectively performing reconnaissance for missions that may not launch for decades or even centuries. Researchers have become particularly interested in mapping dust throughout the Alpha Centauri system. To most people, dust may seem insignificant. But at interstellar speeds, even tiny particles become dangerous. A spacecraft traveling at a significant fraction of the speed of light could suffer catastrophic damage if it collided with dust grains along its path. Understanding where dust is concentrated and how it moves within the system is therefore essential for future mission planning. Webb's observations are providing some of the first detailed clues about these environments. The possibility of discovering planets has only increased interest in future exploration. If Earth-like worlds exist around Alpha Centauri A or B, they would instantly become humanity's most important targets beyond the solar system. Even robotic probes capable of transmitting images back to Earth would revolutionize our understanding of the universe. Imagine seeing the surface of an alien world orbiting another star. Imagine observing mountains, oceans, clouds, or landscapes illuminated by a different sun. Such images would likely become among the most significant scientific achievements in human history. Some scientists have gone even further, envisioning missions that could eventually carry human beings across interstellar distances. While such journeys remain far beyond current capabilities, history repeatedly demonstrates that technological progress often exceeds expectations. Only a century separates the first powered flight from modern spacecraft exploring the outer planets. The gap between impossibility and reality can sometimes shrink surprisingly quickly. As astronomers analyzed Webb's growing collection of observations, they began viewing Alpha Centauri not only as an object of scientific curiosity but also as a future destination. Every anomaly, every dust structure, every possible planetary signature became part of a larger story. Humanity was gradually transforming a distant point of light into a place, a real location in the galaxy with its own history, environments, and mysteries. The nearest stellar system was no longer just a subject for telescopes. It was becoming the first chapter in humanity's long-term journey beyond the solar system. Yet despite all the discoveries already made, the deepest mystery remained unresolved. The more scientists learned about Alpha Centauri, the more they realized how much was still hidden. And as James Webb continued gathering data, the puzzle only became more intriguing. By this point, scientists expected that additional observations would gradually solve the mystery surrounding Alpha Centauri. Usually, that is how science works. New data reduces uncertainty, explanations become clearer, and questions slowly disappear. Yet in the case of James Webb's observations, the opposite seemed to be happening. Every answer uncovered another question. Every new detail revealed additional complexity. Instead of becoming simpler, Alpha Centauri was becoming increasingly mysterious. The nearest stellar system to Earth had long been viewed as one of the most familiar regions beyond our solar system. Astronomers knew its distance with remarkable precision. They knew the masses of its stars, their temperatures, their ages, and the paths they followed through space. Yet Webb was showing that familiarity can sometimes create false confidence. Beneath the surface, hidden processes were shaping the system in ways researchers had not fully anticipated. One of the most puzzling aspects involved the distribution of infrared emissions. Certain regions appeared unusually active, while others seemed unexpectedly quiet. Some structures persisted across multiple observations, suggesting they were genuine features rather than temporary phenomena. Yet no single explanation accounted for everything. Dust explained part of the picture. Gravitational interactions explained another part. Possible planets offered additional clues. But the complete story remained frustratingly out of reach. Researchers began comparing Alpha Centauri to other nearby planetary systems. Some similarities emerged, but important differences remained. In many systems, dust forms broad disks or rings that follow predictable patterns. In Alpha Centauri, however, the presence of multiple stars created a far more complicated environment. The gravitational influence of Alpha Centauri A and B constantly altered conditions throughout the system. Material that might remain stable around a single star could behave very differently here. Over billions of years, these effects may have sculpted structures unlike anything scientists had previously modeled. As new simulations were developed, surprising possibilities emerged. Some suggested that unseen planets could be hiding within regions previously considered difficult to observe. Others indicated that long-term gravitational interactions may have concentrated dust into unusual formations. A few even hinted that the system might contain debris left over from ancient collisions between large planetary bodies. If true, Alpha Centauri's history could have been far more violent than researchers once believed. The idea of ancient collisions fascinated many astronomers. Throughout the history of our own solar system, catastrophic impacts have shaped entire worlds. Scientists believe Earth's moon formed after a collision between the young Earth and a Mars-sized object billions of years ago. Similar events may have occurred countless times around other stars. If Webb was detecting debris from ancient impacts within Alpha Centauri, it could provide valuable insight into how planetary systems evolve over immense periods of time. Another possibility involved objects too small to detect directly but large enough to influence their surroundings. Asteroid belts, comet populations, and dwarf planets can all shape dust distributions through gravity and collisions. In some scenarios, vast populations of unseen objects could be contributing to the unusual infrared signatures observed by Webb. The challenge was that these possibilities often produce similar observational effects, making it difficult to determine which explanation was correct. What made the situation particularly exciting was that scientists were not dealing with a distant, unreachable mystery. Alpha Centauri is our nearest stellar neighbor. Every improvement in telescope technology brings us closer to understanding it. Future observatories will almost certainly study the system in even greater detail. Some planned telescopes may possess enough power to directly image Earth-sized planets around nearby stars. Others may analyze planetary atmospheres, searching for gases associated with biological activity. For now, however, many answers remained hidden. The system continued to resist simple explanations. Webb had opened a door, but beyond that door was a maze of new questions. Researchers found themselves in an unusual position. They possessed more information about Alpha Centauri than ever before, yet they also realized how incomplete their understanding remained. The mystery was no longer about a single signal or a single observation. It had become something much larger. Alpha Centauri was revealing itself as a complex, evolving system filled with processes that scientists were only beginning to understand. And as the investigation continued, one realization became impossible to ignore: humanity's nearest stellar neighbor still held secrets waiting to be discovered. Throughout human history, every great era of exploration began with a frontier. Ancient sailors crossed unknown oceans. Explorers ventured into unmapped continents. Astronauts traveled beyond Earth's atmosphere and stepped onto another world. Today, as scientists study Alpha Centauri through the eyes of the James Webb Space Telescope, many believe humanity is witnessing the beginning of a new frontier, the frontier between stars. For centuries, the stars were unreachable lights scattered across the night sky. They inspired myths, guided travelers, and fueled imagination, but they remained forever distant. Now, for the first time, technology is transforming them into actual destinations. Alpha Centauri occupies a unique position in that future. It is not simply another star system among billions. It is the closest one. If humanity ever develops the ability to travel between stars, Alpha Centauri will almost certainly become the first target. Every observation made today helps build a foundation for that future. Scientists are gradually turning a distant point of light into a real place with measurable properties, possible planets, complex environments, and mysteries waiting to be explored. The process resembles the way early cartographers slowly transformed blank regions of ancient maps into recognizable landscapes. James Webb has accelerated that transformation dramatically. Before Webb, many aspects of Alpha Centauri remained speculative. Researchers relied heavily on computer models and indirect observations. Now, detailed infrared measurements are revealing structures that previous generations could barely imagine detecting. Dust distributions, thermal signatures, and subtle environmental features are emerging from the darkness. While these discoveries have not solved every mystery, they have provided humanity with its clearest view yet of the nearest stellar neighborhood beyond our own. The significance of this extends far beyond astronomy. Understanding Alpha Centauri may ultimately shape humanity's long-term future. Every civilization eventually reaches a point where expansion becomes possible. Thousands of years ago, people expanded across continents. Centuries ago, ships connected distant parts of the world. In the future, advanced technologies may allow humanity to expand into nearby star systems. If that day arrives, Alpha Centauri will likely stand at the beginning of that journey. Some scientists have already begun designing concepts for missions that could reach the system. Projects involving laser propulsion and vision tiny spacecraft accelerated to enormous speeds using powerful beams of light. These probes could potentially cross interstellar distances within decades rather than thousands of years. Though such technology remains experimental, the fact that serious research exists at all demonstrates how rapidly perspectives are changing. Interstellar exploration is slowly moving from the realm of science fiction into the realm of scientific planning. Yet perhaps the most remarkable aspect of Alpha Centauri is how much remains unknown. Despite being our nearest stellar neighbor, it continues to surprise us. The unusual observations made by James Webb remind scientists that even familiar regions of space can conceal unexpected complexity. The system may contain hidden planets. It may harbor environments unlike anything in our solar system. It may even reveal entirely new insights into how planetary systems form and evolve. Every generation inherits a frontier from those who came before. For our ancestors, it was the ocean horizon. For the 20th century, it was the moon. For the centuries ahead, that frontier may be Alpha Centauri. Somewhere among those distant stars could exist worlds that no human eyes have ever seen. Mountains illuminated by twin suns. Oceans beneath alien skies. Landscapes shaped by billions of years of evolution beyond Earth. As Webb continued collecting data, scientists increasingly realized that they were not simply observing a nearby star system. They were taking the first steps toward understanding humanity's most accessible destination beyond the solar system. The mystery of Alpha Centauri was no longer just about strange signals or hidden dust. It had become part of a much larger story, the story of where humanity might go next. And although many questions remained unanswered, one thing was becoming clear. The nearest frontier in the galaxy was beginning to reveal itself, and its secrets were more fascinating than anyone had imagined. After months of analysis, countless simulations, and repeated observations, scientists found themselves facing an unusual conclusion. The most important discovery made by James Webb might not be a specific planet, dust cloud, or hidden structure. Instead, the telescope may have revealed something even more significant, that Alpha Centauri is far more complex than humanity ever realized. For years, researchers viewed the system through the lens of existing models. They believed they understood its overall architecture. They expected refinements, not surprises. Yet Webb demonstrated that even the nearest stars can still challenge our assumptions. The strange infrared signatures, the unexpected dust distributions, the possibility of hidden planetary influences, and the dynamic interactions between multiple stars all pointed toward the same idea. Alpha Centauri is not a static system frozen in time. It is a living environment shaped by billions of years of evolution. Matter moves. Dust collides. Gravity constantly reshapes the architecture of the system. Planets may migrate. Debris may accumulate and disperse. What appears calm from a distance may actually be undergoing continuous change. One reason this realization matters so much is because Alpha Centauri serves as a reference point for astronomers studying countless other star systems. If our nearest stellar neighbor behaves differently than expected, then many assumptions applied elsewhere may also require reconsideration. The lessons learned here could influence how scientists interpret observations throughout the galaxy. Webb's discoveries were not simply about one star system. They were about improving humanity's understanding of planetary systems as a whole. Researchers also began thinking about what future telescopes might reveal. James Webb is extraordinarily powerful, but it is not the final step in astronomical exploration. New observatories are already being planned. Some will possess larger mirrors. Others will use advanced techniques specifically designed to image Earth-like planets around nearby stars. Scientists envision instruments capable of directly observing planetary surfaces, analyzing atmospheres, and perhaps even identifying chemical signatures associated with biological activity. If such technologies become reality, Alpha Centauri will almost certainly become one of their primary targets. The possibility of finding life remains one of the most exciting motivations behind this research. While Webb has not discovered evidence of alien civilizations, it has strengthened interest in the system as a location where potentially habitable worlds could exist. Every new clue increases the urgency of future investigations. If even one Earth-like planet is eventually confirmed within Alpha Centauri, it would immediately become one of the most important objects ever discovered. Yet perhaps the most profound lesson from Webb's observations is a reminder of how exploration works. Humanity often assumes that nearby places are familiar and distant places are mysterious. Alpha Centauri proves that assumption can be wrong. Despite being our closest stellar neighbor, it still contains unanswered questions. It still hides details beyond our current understanding. It still has the power to surprise the scientists who study it most closely. As more data continued arriving, researchers increasingly realized that the mystery was far from over. In many ways, it was only beginning. Every answer uncovered new questions. Every discovery revealed additional layers of complexity. Webb had not solved Alpha Centauri. It had opened the door to an entirely new era of investigation. And beyond that door lay discoveries that future generations may spend decades trying to understand. The nearest stars to Earth are no longer distant lights in the night sky. They are becoming destinations, laboratories, and perhaps one day even worlds that humanity will explore directly. What James Webb found there may not have been what scientists expected. But that is often how the greatest discoveries begin. Not with certainty, but with mystery. As the final observations from this phase of the James Webb investigation were reviewed, scientists found themselves reflecting on an extraordinary fact. The telescope had not traveled to Alpha Centauri. It had not landed on an alien planet. It had not captured photographs of distant civilizations. Yet from a position nearly 1.5 million kilometers from Earth, it had fundamentally changed the way humanity views the nearest star system in the galaxy. What once seemed like a familiar collection of stars had become a place filled with unanswered questions, hidden structures, possible planets, and opportunities for future discovery. The journey began with what appeared to be a routine observation. Researchers expected better measurements and sharper data. Instead, they encountered unexpected infrared signals, unusual dust distributions, and evidence that the system might be more active and complex than previously believed. Every attempt to explain the observations revealed additional mysteries. The closer scientists looked, the more Alpha Centauri seemed to resist simple explanations. That is often the hallmark of a truly important scientific discovery, not that it answers every question, but that it reveals entirely new questions nobody knew to ask. For centuries, humanity could only wonder about the stars. Ancient civilizations built myths around them. Sailors used them to navigate oceans. Philosophers debated their nature without ever knowing they were distant suns. Today, we live in a remarkable era. Telescopes like James Webb allow us to study other star systems in astonishing detail. We can analyze their light, detect planets, examine atmospheres, and investigate environments that would have been unimaginable to previous generations. Alpha Centauri is no longer just a bright point in the night sky. It is becoming a real destination in humanity's understanding of the universe. Perhaps the most exciting possibility is that the story is only beginning. Future observatories will almost certainly surpass Webb's capabilities. More advanced instruments may directly image planets orbiting Alpha Centauri A and B. They may detect atmospheric gases associated with life. They may reveal oceans, weather systems, or entirely unexpected phenomena. What seems mysterious today could become common knowledge for future generations of astronomers. And someday, perhaps decades or centuries from now, robotic probes may leave the solar system and begin the long journey toward these neighboring stars. The data collected by James Webb could become part of the foundation upon which those missions are built. Future explorers may look back at these observations as the moment humanity truly began studying its first interstellar destination. The universe has a way of reminding us how much remains unknown. Even the nearest stars still hold secrets. Yet every observation, every discovery, and every question brings us closer to understanding our place among them. James Webb turned toward Alpha Centauri expecting to learn more about a familiar system. Instead, it revealed a frontier still waiting to be explored. And perhaps that is the most exciting discovery of all. The closest stars in the galaxy are not the end of a story. They are the beginning of one. If you enjoyed this journey through Alpha Centauri and the discoveries of the James Webb Space Telescope, consider subscribing and joining us for more explorations into the mysteries of the universe. Every star has a story, every planet hides secrets, and every discovery brings us one step closer to understanding the cosmos. Thank you for watching, and until our next journey beyond the stars, keep looking up.